Hi, today I want to talk about how it is possible to measure the relative humidity of the air by wrapping a wetted cloth around a thermometer. And that temperature difference is going to be the amount of moisture in the air. So what I'm going to start with is by comparing the mass flux and the heat flux and setting them equal to each other. So in this case, we're going to say that the air is dry. So the initial air is just dry. There's no moisture in it. So let's start with the mass flux side. So we're going to have that heat transfer coefficient and then that concentration difference from the surface and out into the air. And so right here, this is going to be moles per meter squared per second. And that's going to be our rate of mass transfer. Now, we also need a heat source. So let's say it's not our skin or something where it's going to provide a source of heat. Let's say it's maybe something plastic. And so there's not going to be a heat source. So what the heat source is going to be in this case is it's going to be air. And so this is just the heat of vaporization variable. And for water, it's going to be .8 kilojoules per second. Oh, kilojoules per mole. Now, I could also put this as joules per kilogram, but then I would need the molecular weight, and that's just one extra step. So I'm just going to make it easier and just have it in unit, the heat of vaporization in units of kilojoules per mole. Okay, so now let's look. Okay, so now we want to look at the other side for the heat transfer. And so we're going to have that convective heat transfer coefficient, and then we're going to have that temperature from the air to the surface. And so this is the heat flux from the air to the surface, and then if we did have a heat source, we would have that plus Q for that generation of the heat, but in this case we're not going to have that. So now what we're looking at is, let's say that we have a wetted thermometer and it's going to read a temperature that is lower than the thermometer that is wetted, because it's just going to be, if it wasn't wetted, then it would just be reading that air temperature, and then there's no evaporation. So when it's wetted, it's going to be reading that surface temperature. I also would like to quickly discuss a situation when maybe the air wouldn't evaporate, or when the temperature of that liquid surface would be the same as the air. So let's say that we have a pool of water outside, and so the heat source would be the air, right? So what would happen if the water was saturated? The air was saturated, so it's really humid outside, then the water in the pool wouldn't evaporate because the air is already saturated. And so that would mean that the temperature reading for the surface water and for the air would be the same. So let's move on and let's talk about how we can get this concentration difference, how we can get this concentration at the surface more specifically. So what we can do is we can take we can use the partial pressure. So what we would do is moles over meters cubed would equal that partial pressure for the water that is saturated over RT, that gas constant, and the temperature. So that saturated pressure, we would need to find that saturated pressure, we would need that temperature of the water, and we would need to use the Antoine equation. So what we want to do now is we want to relate this back to the Lewis relationship. So through the Lewis relationship, we found that the heat transfer coefficient over that mass transfer coefficient would equal 1 over that Lewis number, and would be that volumetric heat capacity. And so now what we can do is we can plug it in, because we have that that mass transfer coefficient and the heat transfer coefficient. And so what we can do is we can then put the concentrations also in terms of partial pressure. So we have the vaporization, heat of vaporization, and then over here we have that pressure, that partial pressure of that water, that saturated water, over R, and then that temperature at the surface, minus that pressure of water in the air far away from that surface, to that R, and then that temperature far away from the surface. And so for these, we're going to substitute and say that Ts is going to be pretty similar to the temperature of T infinity. Oh my. T infinity to the T average. So we can just use that variable of T average to simplify things later. But first I'll carry on, and I'm going to plug in that density and the heat capacity. And this is going to be the density of the air and water mixture. So that's going to be that pressure total all over the R and then T. And that'll be important later. And then we have that actual temperature difference from the air to the surface. Now I can't substitute these and just say these are both T average, because that would defeat the purpose, and then there is no temperature difference, and that would just be 0. But this is going to be the driving force for the heat transfer. And so we're going to approximate this so that we can cancel things out. And when you get the average of the pressure, the values are when you do the pressure over the temperature to get that average, it's the values are going to be close anyways. So let's start canceling things. So we're saying that these are going to be about T average. That's going to be T average for the mixture of the air and the water. And then we have the R's that are going to cancel as well. And so then we can also we can simplify this now to that heat of vaporization, that pressure of the water, the saturated water, and the pressure of the water minus the pressure of the water further away from the surface, to equal that the total pressure times that heat capacity, and then that temperature difference from the air to the surface. And there we have it. So what I want to do now is I want to circle back to relative humidity. So combining all these concepts. So what I'm looking at here is a infinitely long tube. And then okay. Now what I want to do is I want to circle back to relative humidity. So combining all these concepts and looking at something called adiabatic saturation temperature. And so this is an adiabatic tube, so it's perfectly insulated, and so no heat coming in or out, and it is infinitely long, which will be important later. So you can see here that there is a partial pressure of water vapor, which means that the air contains some moisture. And then, so the water inside is maintained at a temperature just purely because of the flow and the constant supply of water. So it's able to maintain that pressure at that surface. And then this, there's a pressure of water here, the pressure of water, a partial pressure of water that is saturated. That is further away from the surface, and it can be found using the Antoine equation. And so looking out here, we have a partial pressure of water coming out, and that's going to equal, let's enlarge this, and that's going to equal a partial pressure that is saturated for the water at that temperature of the water. And so this water at the temperature of the water temperature at the surface is going to have a vapor pressure. So what else I'm looking at is the pressure, the partial pressure of the water that is at the surface is going to eventually equal the water, the partial pressure of water in the air coming out. So that's because it's an infinitely long tube. So the air is going to become saturated, and the saturated vapor pressure, it's going to become this saturated vapor pressure at the temperature of the surface. And so then what I can do from here is I can make an energy balance, because this is going to be at steady state. And so what that means is the enthalpy in is going to equal the enthalpy out. And then also looking the flow rate for the air, the mass flow rate, is going to equal out, because we are saying it's steady state, and nothing is entering or really leaving the system besides that. So that air is going to be the same coming in and coming out. So what I want to do now is I want to set up this energy balance. So let's start here. So first we're going to look at that that mass flow rate of the air coming in, and then we're going to have to consider the heat capacity, then the temperature that is coming in minus a reference temperature. Then we also need to consider the heat of vaporization, which this is only going to apply to the water vapor, so then we need to make sure to include the partial pressure of that water in the air. And so we're going to put that in joules per kilogram. This heat capacity is going to be in joules per kilogram per Kelvin, and this is going to be in kilograms per second for that mass flow rate. And so then we need that mass concentration. So we can put that in the form of partial pressures, kind of similar to what we did earlier. And so we are going to have the partial pressure of the water, but then we have stuff in kilograms and we want them in moles. So we need to consider the molecular weight and the gas constant and the temperature. And now we want the specific volume, which is just meters cubed per kilogram, because this together is going to be the moles of the H2O over the total meters cubed. So we want the reverse. So we're going to do the inverse and have the RT on top, and then we have the the total pressure times the molecular weight for the air and the water. So it's just, whoa. So that's just going to be M average. So I can just simplify that. So to make this easier, I'm just going to set the temperature reference to 0 so we can cancel that out. And then what this is going to stand for is this is just going to be the mole fraction of water in the incoming stream of air. And so now what I want to look at, well, so this is going to be the in, and this is going to be the out. So what we want to look at is that enthalpy coming out. So we have that flow rate of air coming out. That has to be the same. And then we have that heat of vaporization, the partial pressure of that saturated water, and then we want the molecular weight of that water all over that pressure total over that molecular weight, the average of that air and the water vapor. And then we have the heat capacity and the multiplied by the temperature out. So similar setup to what we have going on up here. Okay, so now what I want to do is set them equal to each other, but I'm gonna move some things around, and I'm just going to have the heat capacities and the total, the temperatures on the right side, and then have those partial pressures on the left. So setting them equal to each other, well, we can also cancel out these errors and cancel out those RTs. So what we can do now is set them equal to each other, move some things around, and we'll end up with the heat of vaporization multiplied by that molecular weight of the water over the total pressure, that average molecular weight, and then grouping those partial pressures of that water in the inlet feed of the air subtracted by the out, what water vapor is in the out air stream. And then the heat capacity multiplied by the out stream, the temperature of the out stream, minus the in. And so we applied Lewis' relation to the heat and mass transfer coefficients, and what we found is that they equaled the rho Cp, that density multiplied by the heat capacity. And so now let's bring that equation back. So which one am I talking about? It's probably over here. So we're going to bring this equation back, except we're going to add, no, it wasn't this one. I actually don't know where it is. I think it was this one. Except we cancel these out. Yeah. And we have the C. This is where it is. The CP. So we're going to keep them as the the concentration at the surface and the air, and then we're just going to say that this is actually in joules per kilogram instead of that kilojoules per mole, so that we end up adding the molecular weight, multiplying it by the molecular weight. So let me just show you. So we have that heat of vaporization, the molecular weight of that water, multiplied that by that concentration at the surface minus the concentration out in the air. We have the density, the volumetric heat capacity together, and the temperature far away minus the temperature at the surface. So that's going to be a major one that we want to keep in mind, and we're going to compare later. And then we have the, we want to put this now in relation to the partial pressures. So I think we did that earlier actually. So let me just write that out again and do it this way. So that saturated water, at that temperature of the water, that RT, the same for that inlet air, but with the water in it. And then we have that total pressure on the other side over that average, multiplied by that average molecular weight. Let's make this bigger. Over that RT, that heat capacity, and then those temperatures for the in minus the out. So then what we have here is, this is the saturated surface temperature, and this is the partial pressure for the water in the air, and then this is the saturated temperature coming out. So what we can do is, looking at these, we can associate these, the parallels. So basically what we're saying that this is the saturated temperature is associated to that temperature at the surface, and then this is just the this represents the row. And now what I want to do is I want to simplify that. So there's some things that I can cancel, like those RTs, the gas constant and the temperature, and let me simplify it now. So the same thing, except we're just getting rid of those denominators. So the only difference comparing this equation to that original one we found before for the comparing the enthalpies is that this is the pressure in, and then this is the pressure in, and then the temperature out is actually first, and then the temperature in is second. So what we can do is we can actually flip those around, and then so it would just be that Pn the water minus saturated vapor pressure at the temperature of the water. And then also flip the T out minus the T in, so that these will negate each other and cancel each other out. So then you can really compare them and see those similarities, and it's actually the exact same equation, except you just move this over to this side. So what's important here is that we can find this equation, but first we can find this variable by calculation, because we know this, we know these, we calculated them before, and these will be measured, and then this one we can find using the Antoine equation. And so what we see here is that so we can see that the temperature read from a wet bulb is just going to be the same as the adiabatic temperature. Just looking at the correlation between these two equations and manipulating them. And the wet bulb is just associated to the same partial pressure of the water with liquid at the liquid temperature. And so how do we circle this back to relative humidity? So let's do that. Relative humidity. With it fully saturated, it will be 100%. Because this is an infinitely long tube. And so what I can do here is I can put that partial pressure of the water far away. The partial pressure of the water farther away from the surface over the partial pressure of that water at that temperature of that saturated vapor pressure of the water at that T infinity. And this will all equal 1 because it's 100%. So that's how we can relate this all back to relative humidity. And so this will be able to be calculated, and that's how we would get this.